Hello and welcome once again for another EE324 video. Today we'll be discussing electromagnetism continued, and we'll practice a couple of things, electromechanical systems continued, and we'll practice a couple of things from previously. So suppose we have the following type of system where we have a nice little mass that's connected to a spring. It feels an electromagnetic force whenever it is close to the inductor coil here. There's a separation distance d between these two things, and this is obviously our idealized circuit that we have over here. What we're going to do this time is actually we're going to have some nonlinear force that's occurring here. This is a bit more realistic than what we've been doing before. So the force that the cart feels from the electromagnetic force that the cart feels is related to the current squared, and then obviously the distance between the inductor coil and the position of the mass. Okay, so this is a bit more like you might have seen in electricity. You know, we learn that a lot of these forces, they decay as the square of the distance, things like this. Okay, so we have to model the two pieces. So we have, the first thing is, the first part is the circuit. So I'm going to bring that over here by KVL. We know that Vn minus Vr minus Vl is equal to 0. And I'm going to call this current. I'm going to call it IL. Okay. So then by Ohm's law, we know that this is going to be Vn minus IL times R minus VL equal to 0. And we can finally solve this out nicely, and we get IL dot LIL dot plus IL times R equal to Vn. Okay, so this is pretty simple. The cart is also going to be simple. I'm actually going to switch here to a different color. By now, you should recognize that this is just going to be mx double dot plus kx is equal to FEM. But in this case, we are going to replace FEM with this kfi squared over d minus x squared. So and this is going to be IL because that's the current that we're dealing with here, over d minus x squared. Now notice that we have over here, we have an x squared term, and we also have an IL squared term. So this is obviously nonlinear, this input function here, but the differential equation itself is nonlinear with respect to x, for instance. So we're going to have to account for that in a bit. Okay, so we have these two equations, and what I'm going to do is I'm going to put this in state space. So I'm going to let IL equal to x1. And this means that x1 dot is equal to Vn over L, I believe. Yeah, over L minus something times x1 here, R times x1. Okay, and then I'm going to let x2 be equal to x, which implies x2 dot, oh, and I should say x3 equal to x dot, which means x2 dot here is going to be equal to x3. Okay, and then finally, since x3 dot is equal to this, let's go back and look at what we had. X3 dot is going to be equal to x double dot, and if I solve this, so if I solve this equation for x double dot, what I should find is I get minus k over m times x plus kf il squared divided by m times d minus x squared. Okay, so that's what I'm going to get. K over m times x is x1, so this should be x1. Oh, sorry, x2. X is x2, so x2 and x2. So this is going to be x2 plus kf times il squared over m times d minus x2 all squared. Okay, so if I write this out now, I can write the whole state space. x1 dot is equal to Vn minus R times x1 over L. x2 dot is equal to x3, and x3 dot is equal to minus k over m times x2 plus il. Ooh, I forgot to put this in here. This is x1 squared. So plus kf times x1 squared over m times d minus x2 all squared. Okay? So now I'm going to make this next part simple, but you could obviously make it a bit more complicated if you wanted. What I'm going to do is I'm going to linearize. But how I'm going to make it simple is I'm going to linearize around nominal input voltage Vn equal to 0. So with no input voltage. Now, obviously, that's going to make things pretty simple here, and we'll see that in a minute. So basically, then to find the fixed point, we can do this. We can say x1 dot is equal to, well, this is going to be 0 for Vn minus R times x1 over L. And we want to find when this is equal to 0, because at the fixed point or equilibrium point, or operating point, whatever you want to call it, then I need all of these x dots here to be equal to 0, basically. So here, that's where there's no motion. So here we can see pretty easily that x1 is equal to 0. That's going to be true without any input for the rest of these as well. X3 equal to, x2 dot equal to x3 equal to 0 implies x3 is equal to 0. And then x3 dot equal to kf times x1 squared over m times d minus x2 squared minus k over m times x2 equal to 0 implies that if I substitute in 0 for x1, and this implies that x2 is also equal to 0. Okay? All right. So then our fixed point is going to be 0, 0, 0. To find the linearized model, we need the Jacobian. At the fixed point, of course. So basically what we're going to find is we're going to have delta x vector dot. It's going to be equal to j times x plus, in this case it's really just going to be some matrix b times u, b times delta u, where it could have been a vector, but in this case b will be a vector, but delta u is not. We only have a single input here. So j in this case, this is going to be times delta x. J is going to be equal to the Jacobian matrix. And what we need to do then is we need to look at this and find the derivative of this with respect to x1 and x2 and x3, right? So we have to, and that's for each of these, x1 dot, x2 dot, x3 dot. So the first one, there's only an x1 in here. So if I take the derivative of for this top piece, if I take the derivative of this with respect to x1, what I'm going to find is that I get minus r over L. So that's what I'll put down here. But there's no x2 or x3, so this is just going to be 0, 0. For the second one, there's only an x3, and it's not multiplied times anything, so this is going to be simple. The third one, I do have to do a little bit of work. So if I take the derivative of this with respect to x1, then obviously this is going to be 2 times kf times x1 divided by m times d minus x2 squared. Oh, oops, this was m. There's no, oh, there is an x2 here. There's an x2 here, and it's in both of these. Notice here and here. And there's no x3 though. I'm going to need a little more space than this. So this is going to be, I'm going to do the easy part first, minus k over m. And then when I take the derivative of this one, what you should find is you get kf times x1 squared, because obviously I'm doing this with respect to x2, so there's no derivative that happens there. Kf times x1 squared divided by m times d minus x2 cubed, and there's going to be a minus sign as well, so it's going to be minus okay. Actually, it's going to be plus now that I think about it, and there's going to be a 2 here. Because the minus 2 and then the derivative of the inside here gives me minus 1, so the minuses cancel. And this should have been, this 2 should be down here. No, that was right. Okay, so that was that term. This was 0, 0. And then over here we have 0, 1, 0. Okay, so that's my Jacobian. When I multiply that times, and I have to evaluate this at the fixed point, which is 0, 0, 0. So when I evaluate it at the fixed point, several of these terms are just going to go away. This one's going to be 0 because obviously at x1 equal to 0, that makes this whole thing 0. This is minus k over m because, again, same argument there. And then this is 0. Okay? So since this is evaluated at 0, 0, 0, this is what I get. And my linearized model then is as follows. Delta x dot is equal to minus r over L, 0, 0, 0, 0, 1, 0, minus k over m, 0, delta x, plus this one was, I didn't show it, but this was pretty easy, times delta u. Because obviously the input term is linear, so when you linearize it, it just becomes a linear term delta u, right? With the appropriate multiplication that happens there. Or I could write this as delta x1 dot is equal to minus r over L delta x1 plus 1 over L delta u. Delta x2 dot is equal to delta x3, and delta x3 dot is equal to minus k over m delta x2. Okay, so then obviously we can ask about the stability. So we need to find the eigenvalues of j of x. So we need to find the determinant of this matrix. and we need to set that equal to 0, because that's how you find the eigenvalues. And you should see pretty quickly that the determinant of this matrix is just this. Because these zeros here kind of take care of these terms down here. So and we're going to set that equal to 0. If I multiply all of these out, or if I can add all of those terms to the other side, so I get everything positive. Now it seems like we're kind of stuck here, and in a sense we are, because I wouldn't be able to ask a question about this more generally with a cubic, trying to solve a cubic, because the cubic equation is much more complicated than the quadratic equation. There is an equation just like the quadratic equation that can solve these, but it's so ugly to write out that I wouldn't ever ask you to do so. So instead what I'm going to do is I'm just going to substitute in some values here. So I'll say r equal to 4, l equal to 3, k equal to 2, m equal to 1. And I've obviously skipped the units here. This is henries, this is newtons per meter, I think, and this is kilograms. So there's my units. What I'll get is lambda cubed plus 4/3 lambda squared plus 2 lambda plus 8/3 equal to 0. And what I found with the roots is function is this is lambda equal to minus 4/3 plus or minus the square root of 2 times I. Okay, so those are my 3 eigenvalues, and if I plot these eigenvalues, what I get is something like minus 4/3 and plus or minus square root of 2. This is going to be the imaginary axis. And this is the real axis. So then I get these. This is my plot, and obviously this is a marginally stable. Because these have 0 real part, and this has negative real part, okay? So marginally stable. That's all that I have for this video. Hope to see you again soon.